Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to apply Newton's laws for general plane motion. And what we're looking at, we've got this 4-meter beam here that's 10 kilograms long. Let's imagine it's hung by these two strings, both of which make a 30-degree angle with the horizontal. And we're going to imagine that this string on the left here breaks. And what we're going to try to do is calculate the angular acceleration of this bar, or this object, and the acceleration of the point G. So G being the center of gravity of the object. So what we're going to do is we're going to start with a free body diagram, and since this is broken, this string here, I'm going to just get rid of this now. And when we draw our free body, we got to keep in mind that we're going to have kinetic terms, I alpha terms, and MA terms. So before I actually draw a force free body, what I'm going to do is I'm going to take this object and I'm going to clone it, make a second picture that I'm going to use for the kinetic part of the diagram. Alright, whoops, put that back where it was. Alright, so now free body. In this picture, what I'm going to do is I'm going to put all my force vectors. First force vector that comes to mind, the gravitational force, which is basically straight down. I'm going to go ahead and put an mg for that. In addition to that, we've got a tension applied here, up and right. So I'm going to go ahead and put a force vector for that. Now the length of this tension doesn't have anything to do with the length of this rope. So I went ahead and kind of deliberately made that force a little bit longer. And that's pretty well it. Those are the only forces I can think of that are acting on the system. All right, now let's talk about the kinetic part. So this thing will probably have an acceleration vertically. I say probably, definitely have an MA down. So I'm going to call that MA. Now that acceleration is going to be the acceleration of G, the center of mass of the system, y direction. It's also likely going to have an MA term to the right. So I'm going to call that one MA sub GX. Now in addition to that, this thing's going to start rotating faster and faster and faster, so it's also going to have an I alpha term. So the kinetic part of the diagram's got these three terms. We've got the MAG sub X, MAG sub Y, and an I alpha term about the center. So there's our Newton's second law analysis, or I'm sorry, there's our free body diagram for applying Newton's second law. Here's our picture with all of our forces. Here's our picture with the MA terms. All right, so let's start writing force equations. So, equation number 1, sum of all forces x direction equals MA in the x direction. I'm going to go ahead and call right positive. So the force component of this tension to the right is going to be T cosine 30. That's the only force in the x direction, so equals MA. Now that acceleration is the acceleration of point G, x direction. Next equation, force equation y direction, sum of all forces y direction equals MA. I'm going to go ahead and do down positive. If you've seen some of my previous videos, this is my standard rule of thumb. Identify the acceleration direction. If you can, call that positive. Center of mass most definitely is going to accelerate down, so I'm going to go ahead and call down positive. So that force equation is going to be mg minus the y component of this guy, T sine 30, equals MA sub G, y direction. All right, next, we've exhausted our force equations. Now we're going to write a moment equation. And there's a couple places I could sum moments about. So let's see, sum of all moments. I'm going to do counterclockwise positive. I'm going to go ahead and just sum moments about point G here. So sum of all moments about G is equal to I alpha. Now, the reason it's just I alpha, if I sum moments about G, this is the only kinetic term that we're going to need to include, because the MAX and the MAY go right through G. If we had summed moments about this point, would be another logical alternative, right? the net moment, we'd have mg times L over 2. And then in this diagram, the sum of the kinetic moments would look like this. We'd have an I alpha, plus we'd have an ma sub y g, or mag sub y times L over 2, both positive. This term would not provide a kinetic moment because there's no moment arm. This term goes right through this point. But anyway, those are the two logical places to sum moments about this point or this point. I'm going to go ahead and sum moments about g, in which case the only term I'm going to have is the I alpha term. So that equation is going to be, let's see, t sine 30 times the distance L over 2. Right, that's the moment arm for that force. That's that distance in the picture, is equal to I alpha. Now I'm going to go ahead right now and just do this. The I, moment of inertia, treating this like a long slender bar about an axis that goes through the center, is 1/12 ml squared. So there is our Newton's second law for rotation applied about g. All right, so what we have now is a system of equations here. We've got equation 1, equation 2, equation 3. Let's take a moment now and just kind of glance these over and think about knowns versus unknowns. The tension is not known. Now you might be tempted to say, well, t sine 30 plus another t sine 30 minus mg equals 0, and that was true when this was static, before that rope broke. But that's not true at this instant now. That tension is no longer there, and it's no longer a static problem. So the tension is definitely an unknown. Same thing with agx, agy, and alpha. So this system of equations has 4 unknowns, and that's a very important thing to take note of. Because it has 4 unknowns, that means we don't have enough information yet to solve it. So what I'm going to do here is I'm going to shrink this down just a little bit, give myself some more room here, put this to the side. We got to come up with a 4th equation. And the 4th equation is not going to come from Newton's second law. It can't. We've already exhausted our Newton's second law possibilities. So the 4th equation we're going to get is going to be a kinematic equation. All right. An equation relating motion, or an equation about the motion of this beam. Now, I'm going to go ahead and take a look at another point here on the right end. I'm going to call this point R. And here's something I know for sure about R. Because this is fixed by a rope here that's not breaking presumably in the problem, the acceleration of R can only be this way. And I'm just going to call that A sub R, and this would be a 60-degree angle. And I'm going to actually go back. I'm going to put acceleration vectors in red. So the acceleration of point R is in that direction, and that would be 60 degrees. This would have to make a right angle to the tension unless this rope stretched or broke or something like that. But as long as this rope doesn't break, we know that the acceleration of that point is in this direction. It's important to realize it's not moving at this instant, so there's no centripetal term. If this thing were already moving, we could perhaps have a centripetal along the rope, but at the instant shown, it's not yet. The acceleration of g is downward. Whoops. Straight down at the instant shown. Whoops. Well, I should say the y component of g is down and the x component is to the right. And I can write a kinematic equation relating the acceleration of g to the acceleration of r. And that equation would look like this. The acceleration of g is equal to the acceleration of r plus the acceleration of g with respect to r. Now, the acceleration of g looks like this. It has an x component, I direction, and a y component in the minus j, equals. The acceleration of r I don't know, but what I can do here is I can write it in component form. I'm going to go ahead and write this acceleration in terms of ijk, a standard xyz coordinate system. So this is going to equal acceleration r cosine 60 to the right. Right, that's the x component of this acceleration vector, minus acceleration r sine 60 in the j direction. You can see already I'm going to need more room. right? Now we'll talk about this guy, acceleration of g with respect to r. Now that g with respect to r could conceivably have two terms to it. You've got alpha cross r terms, and you've got omega cross r's, or I think I usually write them r omega squared terms in the minus r hat direction, right? Centripetal acceleration and tangential accelerations. At the instant shown, this bar is not rotating yet, so we're not going to have a centripetal term. We're only going to have this alpha cross r. So I'm going to go ahead and write, all right, alpha. Now my angular acceleration is this value. It's in the plus k direction, crossed with the position vector of g with respect to r. Now that distance is L over 2, and it's in the minus I direction. So let's do L over 2 minus I. Okay, equals. Now I'm going to rewrite this. Acceleration gxi plus acceleration gy direction in the minus j. See, I was forgetting a g here. This acceleration was for point g, y direction. Equals, this we're going to leave alone, a sub r cosine 60i, minus this we'll leave alone, a sub r sine 60j. I want to just think about that for a minute. That thing was down, yep, okay. Plus this term. All right, so now we're going to have alpha k cross L over 2 in the minus I. So that's going to be alpha times L over 2, and our direction is going to be k cross minus I. And if you do right-hand rule on that, I get minus j direction. Okay, next, let's compare directions here. So we've got an I component here, and that is the only I component on the left-hand side. Right-hand side, we've got this guy. Nothing else in the I direction, so this equation stands. All right, Y direction, or J directions. Now you notice there's a minus sign here, minus sign here, minus sign here. So I'm going to go ahead and write this without the minus signs. So we're going to have this equals this guy, r sine 60, whoops, not r sine 60, acceleration of r times sine 60 plus alpha L over 2. So there's our two equations. Okay, I'm going to take a moment now and kind of think about the algebra and work this out. I'm going to pause the video and just come right back. Okay, folks, I'm back and I worked this out. Now this video is at 13 minutes, so I think what I'm going to do here is I'm just going to outline the algebra here and not actually include that in the video, because the point of the video is how to write the equations of dynamics for the system, and this is how we write the three force equations, and here's how we write a kinematic equation relating g to r. But let me outline the solution I've just worked through. So you can take this and sub it here. Rewrite the equation. Then you can take this, actually use green here, and sub it here, rewrite the equation. And then you can just leave this third equation alone. Now your new system of equations, I'm going to call this our equation 1 green, as in after you did the substitution, and then equation 2 green after you do the substitution, and this guy you can just leave alone for now, 3. Your new system of equations will have 3 unknowns: tension, alpha, and the acceleration of r. Now I know you might say, well, we don't want the acceleration of r, and that's fine. I probably could have redone it to made it maybe acceleration of g, but it's fine the way it is. I worked it out. It was quite a bit of algebra, and I did finally get it worked out. And here's the values that I got. Let's see, I'll write them down here. I ended up with, whoops, a sub r equaling 4 meters per second. I ended up with an angular acceleration of 1.75 radian per second. I ended up with an acceleration then for g, because they're directly related. Once you have the a sub r, you would have g here. Oops, gx I mean. I believe that was 2. Yep, 2 meters per second per second. I ended up with an acceleration g y direction then of 7 meters per second and a tension of 23 newtons. So again, going through the algebra, and I'm not going to include this in the video, it's already at 15 minutes, but after you make these two substitutions, you'll get a new system of equations. So the new equation here I called equation 1, the new equation after substitution here, equation 2, this third one I'm just leaving alone, calling it equation 3. The new system of equations will have known unknowns t, alpha, and a sub r, the acceleration that I call r here. When you solve that system of equations, I did it just by substitution. For the tension, I got 23 newtons. For the alpha, 1.75 radian per second. For the a sub r, 4 meters per second. Then to get the agx and the agy, we can go to our kinematic equations here and here to find those values. So here's the solution I got for this system. Hopefully it's right. This is not one that's out of a book or anything. I just made it up off the top of my head. But these values all look reasonable. I'm going to assume that these answers are correct unless one of my students finds an error in this video. So I hope that this helps demonstrate how to work a problem using Newton's laws and kinematics basically for general plane motion. So have a great day.